afternoon, everyone. My name is Rikith Reddy. I am a data scientist at Arista Networks. This is my very first time at the WLPC, and it's an amazing place to meet a lot of people. Thank you. So I was talking to a lot of folks here, and one of them happened to be Chris. I bumped into him the other day. He's there. Hi. So we were discussing a couple of interesting problems which we are trying to solve on the wireless networks today. He mentioned that the client application experience or client quality of experience is one of the most interesting problem which needs to be solved. So that is exactly the topic of my presentation today, where I'll be walking through how we at Arista try to find the quality of experience of clients in the network. So just to set the context of what this problem is, let's say you have a user called Sam, and he is browsing on the internet using Wi-Fi, or he's watching YouTube, and maybe he's watching a couple of cat videos which he likes, and suddenly something bad happens and his Wi-Fi doesn't work. Sam is not able to see his cats which he wants to have a look at, and he is pissed off. And what would a user usually do if his Wi-Fi doesn't work? He just complains to the network administrator that your Wi-Fi sucks. This is something which commonly happens, and the network administrator wants to debug this issue. So what we usually do in this case is we go about looking at all the wireless parameters, and that's what the network administrator does in this case as well. She looks at the RSI, the data rate, and the retry rate for the client. But in this particular case, she finds that all of them are amazing. Like, there's no issue with Sam's Wi-Fi. But still, Sam is complaining that he's not able to browse YouTube. So what is the issue here? The network administrator is confused what's happening. So if you might have faced this in your networks, can someone tell what might have been happening in this case? Why Sam is facing an issue? Yeah, it's not the Wi-Fi. Yeah, but how will the network administrator know it's not the Wi-Fi? It might be a problem on the YouTube's end or some other server, some other switch which is sitting in between. And there's no way for us to know, looking at the wireless parameters, that this is an issue. We are not able to debug that. So that is the exact problem we are trying to solve. So this problem arises because the user does not care that his wireless parameters are good. Let's say his RSI is good, his retry rate is good, but he doesn't care because he's not able to access YouTube. So from here, what you can understand is the user's experience is only related to his application experience. If his application does not work, he has a bad network experience. If his application works, then he has a good experience. So we have a direct relationship that the network is perceived by the user only by the applications he's browsing. So then we can ask this question that what if the network administrator can figure out that the application experience was bad for that user? Can the network know if the application experience of the users in the network is bad or not? So we also were looking at this problem and trying to solve this, and we spent quite a bit of time on this, and we wanted to look at the most popular applications over the internet and see if we could find something. So the most common traffic in the internet today is from the web applications. There are a humongous number of web applications which are out there, so we just started analyzing them. We were trying to look at the quality of experience of all these web applications. So what did we do? We just had a couple of laptops, and we varied the network conditions and just checked how these web applications perform in different network conditions. We captured the experience of the users and also the packet traces of how the network was behaving in this situation. And then we started analyzing them once we had a lot of data. So here is a summary of that particular analysis, where the first thing we found is that most of the traffic on the internet for the web applications is of TCP. This is nothing new. We already know that. So what we decided is to have a closer look at what TCP is doing. So once we had a closer look at this, so whenever a user had reported bad experience, or there was bad experience which was indicated by a person using the network, we saw a lot of packet retransmissions. So if there were packet retransmissions, the user was reporting bad experience. So we wanted to have a closer look and just have an intuitive idea of why this might happen. Let's say you're browsing you're opening a website, and the browser opens and there's a packet drop. and you'll see that loading screen which the user doesn't like. So as long as he keeps seeing that loading screen, he doesn't like it. So that happens because of a packet drop. TCP is a byte stream which requires all packets to be in order. So whenever there's a packet loss, the user sees that loading screen. So that's how this is intuitively made. So our question was, if we are able to detect these retransmission events on the access point, we solve this quality of experience issue. So because the user is waiting, as long as the user waits, he's having bad experience. And if we are able to detect if the user is waiting, we have solved the issue that the user is feeling bad, the application is bad. So that's what we did, and here is, and we came up with this algorithm called the web QA algorithm, obviously because we are analyzing web traffic. I'll try to give a very simple understanding, a breakdown of what's the core or the fundamental of this algorithm, so that you get an idea of what we're trying to do. So for this example, I'll be taking a taking a simplified version of a TCP packet. So I'll be taking these three parameters, that is sequence number, the acknowledgement number, and the payload length. Sequence number is a counter which indicates which byte of the data is being sent. ACK is the amount of data which has been received by that particular host, and the payload length is the amount of data in that particular packet. Let's take a scenario where there's a client connected to an access point, and he is trying to load a web page from a server. So what happens in this scenario? So what TCP does is it sends something called as a window of packet, TCP window. So why does this happen? TCP is a reliable protocol, and it requires every packet to be explicitly acknowledged. So, but if you do the raw implementation of this, you send a packet, you wait for the acknowledgement, you send a packet, you wait for an acknowledgement, which is an overhead. And you would not like that. So you have something called as a TCP window, which tells you how many packets you can send over the network without receiving an ACK for it. So that's what the server is doing. It's sending a packet, sending a window of size 5. The first packet has a sequence number of 1, ACK number of 1, and a payload size of 1. I made this so that it is simpler to understand. In reality, the numbers might be very different. So once the client receives the first packet, which is detected on the access point at time t1, it responds to it. The response is with an ACK acknowledgement. The acknowledgement can be found with the addition of the sequence number and the payload size of the received packet. So if you see that number 2 over there, that is the acknowledgement number of that particular client. So what it is telling is that I have received all the data till 2, and the next sequence number I'm expecting is 2. So that's what is being conveyed through this message. The server sends over its next packet at time t3, and as expected, the client responds with an ACK number of 3. Let's say there was a packet loss due to some network condition, which can be anything. But what happens in this case? The server will not stop sending because it has more window to just send over the packets. It goes ahead and sends the 4th packet. What will the client do when it receives this 4th packet? Client said that it is expecting a sequence number of 3, but the server sent over a sequence number of 4. It will just send something called as a duplicate ACK. Duplicate ACK is nothing but the acknowledgement number, which is same as the previous acknowledgement number. So basically what the client is trying to convey here is that I want a sequence number of 3, but you send me something else. But maybe the server did not see this or ignore it. It just sends over the next packet as well, because it does not need an explicit acknowledgement for that as well. On seeing this, the client again says that I'm looking for 3. In this situation, multiple things can happen. Let's say there's a TCP retransmission timeout, which says that just resend this packet, and server understands that the packet number 3 had been missed. And what happens is it just retransmits the packet. That is called the retransmission. And the client is happy, it has received everything, and it sends over an acknowledgement for 6 if it had been using TCP buffering. So what we need to see here is from the point of view of what happens when an application user is using this TCP connection. Let's say the first 2 packets represent the title of a web page the person is trying to load. He sees that text on the browser. The 3rd, 4th, 5th maybe represent an image, but the 3rd packet is lost. Even though 4 and 5 have been received, the browser cannot make any sense because it needs all the bytes in order, and 3 is missing. So the user just sees a loading screen. And if you can have a clear look, this duplicate ACK is an indication of a packet loss in the network. We'll be able to detect it if you just go through and see the ACK numbers on the access point. So at time 6, we'll be able to detect that there has been a packet loss. And at time t10, since there's no more duplicate ACK, you can infer that the packet loss has been recovered. So if you just take this particular time, that is t10 minus t6, it shows an approximate indication of how much time the user has been waiting. So this is very useful because it's kind of giving you the idea of what the user is seeing and like how the application from his side is behaving. If you want to have a closer look on what you can monitor on the access point for this, is something like this. Like let's say you're just monitoring all the ACKs being received from one side of the client. At time t2, you would see an ACK received as 2. There is no previous ACK, let's say it's a very clean state. At time t4, you would see the ACK received as 3, and the previous ACK you see is 2. It's different, it's not a duplicate ACK, you can go forward. But at time t6, you see that the previous ACK and the current ACK which you received are same. You can start flagging this, like let's say a very fundamental version of this algo can flag this, right? You have seen the same acknowledgement, and duplicate packets are a result of a packet drop in the network, at least from that what TCP says. You see at time t8, the same situation is there, the ACK is same as the previous one, and you can still infer that the lost packet has not been recovered. At time t10, you see a different one, and then you can infer that this has been recovered and the TCP is just doing its job after that. So you get the recovery time, or the time spent by the user, approximately as t10 minus t6. So this is a very simplified version of the algorithm, but if you go and try to implement this, you'll turn into a lot of complications. I cannot fit all of them into this presentation, so I tried to pull out a couple of things which can help you understand what kind of issues you run into when you're implementing this. So the first one is you check the acknowledgements being sent from the server. The first ACK is 1. The second ACK is also 1. Would you be flagging this as a duplicate ACK? Like, is this because of a packet loss, or is this expected? Maybe someone can, right? Is this expected, or is it a duplicate ACK? It's expected. Yeah, it's expected because the client is not sending any data. The acknowledgement is just sequence number plus the payload size. And since the payload size of the client is 0, this is expected. So you need to maintain an additional variable which talks about if this particular ACK you're getting is expected or not before you check for the duplicate ACK and flag it as a retransmission. This is one issue, and there are more common questions even about this. So what we are talking about here is a single TCP connection, but modern applications might not be using a single TCP flow. Modern applications have multiple TCP flows just to be more efficient. So so more common questions which come up when you're talking about this is modern applications have multiple flows. You're talking about bad time, but how does it make sense in the whole context? Let's say I'm using Google Docs. I type for 5 minutes. I go away from my keyboard and come back and type again after an hour. I've used the application just for around 5 or 6 minutes. In contrast to, let's say I'm watching a YouTube video for an hour continuously. These both cases are different. If I report the user's bad time as 2, the impact of both of them is different. In YouTube's case, it would be maybe nothing, but in Google Docs' case, it would be more because the user has used it for less time. So how do you solve this when you're looking at this from the point of view of an access point? So you would have flows, something which look like this. Let's say all these flows belong to a particular application. What you can do is find the most common interval where these flows are active. So one assumption here is that we are able to tag that these flows belong to a particular application. This can be achieved in a lot of different ways. One common way can be you can just maintain IP port mapping. And I'm just assuming that these flows can be identified as an application. Once you do this, you can have an information of approx information of how much time the application was used. But I made another assumption here. I'm just saying that I'm able to detect the difference between this, which is not so easy. how do you detect this idle time? We have a separate version implementation of an idle time. So how do you detect this is we are going by TCP's IEEE standard. Someone was making fun that this is not implemented directly yesterday in the hacking session, that a TCP's flow should be replying with an ACK within 500 milliseconds. So since most commonly we do not use the exact IEEE version, we have added a particular buffer, let's say 500 milliseconds plus X milliseconds. If there's no activity on the network for that particular app, the app is idle. In case of Google Docs, all you'll be seeing is an idle flow. There'll be nothing on the network for that particular application. And you'll be just seeing some keep alive packets from TCP, but you can just choose to ignore them. So that's how we have this idle time detection, which is giving you an idea of how much time that particular app was active. Next, you can again run this common interval thing on the places where you found bad flows within those multiple flows, and you can get a proper idea of how your application was looking throughout that time. So the next question people ask when I'm talking about all this is that this has a huge performance cost. Like, how do you manage this? Like all this looks like a lot of computation, a lot of memory. But but if you look at this is just doing simple computations and just packet inspection. And when we implemented the same thing on Arista's access points, we found that we were able to do this within 0.5 to 3 KB of memory usage per application. And we assumed around 100 clients. And the throughput impact was 1 to 3%. This is just assuming that you already have that application detection running. So this is over the application detection running. So talking about how important this problem of QoE is, you would like to trade off 3% of your throughput just to detect if the user is facing bad application experience. So how did we do? So all this was theoretical and maybe some experiments. We also wanted to test if it works in a real world scenario. And we had to come up with a testing use case which helps us understand if this thing really works. So here's how we did the testing for this web QoE. We had a client device which is running a browser, and it was trying to just load a website, google.com in this case. And what we did is we did a page load time capture from that browser. And we also did a packet capture on the network device. And we started varying network conditions throughout. The reason we took page load time is because that is the experience, that is the direct relation to your experience, right? Like if the page is taking too long for you to load, you have a bad experience. As it keeps going on, you feel more uncomfortable. So the results of this look something like this, where for the first time we varied the bandwidth from 0 to 50 kbps for that particular client. And we see that there's a reverse relationship that as you keep increasing the bandwidth, you're able to load Google easily. This is not that interesting, but the next one is more interesting. The recovery time or the bad time we're computing, that is on the y-axis, and on the x-axis you have the page load time, which have a direct relationship. So you see a direct relationship between the page load time and the recovery time. And I stated that how the user is seeing your network is with respect to how long his page is loading. And we are able to capture it with this particular metric. So this is a direct indication of what the user is feeling for your network. Another experiment we did was just induce packet drops, random packet drops in the network, and see how this particular algorithm behaves with respect to that. So you see this graph where we varied the packet drops from 0 to 20% around. It's a huge number. And we just noted down the recovery time of that particular thing. So we could see that it has a linear relationship again. But the more interesting part comes here when we look at it from the point of view of the page load time again. You see that you have a direct relationship again. So with this, we were sure that we are able to capture the user's experience somehow with this algorithm, and this acted as a benchmark. After this, so if you wanted to have a look of how an application would look in a bad network, your application would look something like this. If you start plotting it on the x-axis, you can have aggregated versions of time, aggregated metric of your recovery time or the active time, and y you have the duration. You would see something like this. Your active time and bad time vary something like this in a bad network. But when you look at it in a good network, you see that the bad time is not present. So what we did here was we are able to detect the quality of experience of web applications. But there was nothing used with respect to only web applications. All the algorithm was using was basic things which are available in a TCP protocol, and this can easily extend to any TCP app that's out there. And we have been using it for SSH and different applications, and it works fine. So now going back to Sam. Let's say Sam complains that the Wi-Fi is bad to the network administrator. What would the network administrator do with this particular thing implemented in the access point? Your Wi-Fi KPIs look good. We already say this. But there might be a non-Wi-Fi issue because the XYZ app you're using, because we are able to detect the application as well, has some issue across the network with different users. So there might be an issue. So if you had a dashboard, something like this, where you had the experiences capture of different applications, you could show that maybe Apple services had the bad experience as shown in the bar. Green is good and red is bad. The Apple services you have been using might have some issues. And you could also show that if there are multiple clients, a lot of clients also face this issue. And the application, like you can also benchmark it with the application usage and get to know what's exactly happening in your network. And since someone said, what is the issue, and the ability to tell from the network administrator side that this is not a Wi-Fi issue, the problem is with you. So this gives you that power. And yeah, thank you.